Stemridge's and Heyman's results on monomial traces help us to understand symmetric functions a little bit better. So recall that we take a Hecke algebra element, we can define a symmetric generating function for characters evaluated at that element. So we define yq of g to be the sum of induced sign characters evaluated at g times monomial symmetric functions, which also happens to be the sum of monomial traces evaluated at g times elementary symmetric functions, which also happens to be the sum of irreducible characters evaluated at g times shear functions, etc. Whatever symmetric function basis, we expand this in, the coefficients are certain trace evaluations. So it's natural to ask which symmetric functions in C bracket Q tensor symmetric functions are yq of g for some g in the Hecke algebra. It turns out if we extend scalars a little bit further than this, then we have the following. Every symmetric function in Z bracket Q tensor degree n symmetric functions is yq of g for some g, here's where we extend scalars a little bit, in rational functions in Q with rational coefficients tensor the Hecke algebra. Now remember, rational functions are polynomial in Q over polynomial in Q. And we could assume these polynomials have integer coefficients. We can get any rational number by taking integer over integer. So to see this, let's choose a symmetric function in Z bracket Q tensor degree n symmetric functions and write it in terms of elementary symmetric functions. So we'll write it as sum of a lambda of q elementary symmetric function e lambda. So these coefficients can be polynomials in Q. And let's define a Hecke algebra element G by letting G be a sum over permutations, let's say mu, over partitions mu. A mu of Q over the product of the parts of mu Q factorial. All of that times the Kaj-Down-Lustig basis element indexed by W mu, the longest element in the Young subgroup S mu. And now let's compute YQ of this element G. So this is a sum over all lambda phi lambda of this element, sum over mu, a mu of Q over the product of parts of mu Q factorial. Times the Kaj-Down-Lustig basis element. All of that times E lambda. Now phi is a linear function. We have a lot of scalars in here, so we can really slip that right next to the Kaj-Down-Lustig basis element. So this is a sum over lambda of a sum over mu of coefficients times phi lambda of C tilde W mu Q, all of that times E lambda. But this evaluation by Heyman and Stembridge's result is non-zero only when lambda and mu are equal. And in that case, this is equal to a product of Q factorials of parts of mu. So first of all, it's zero if lambda and mu are different. So we don't need to sum over all pairs lambda and mu. We only need one partition. So we've got sum over partitions mu. Now we've got a mu of Q over this product of parts of mu Q factorial. And then this evaluation turns out to be parts of mu Q factorial. And then we have E lambda, or E mu on the end, because we're only looking at the mu term. And then these q factorials and those q factorials cancel. And we're left with the sum of a mu of q e mu, which is precisely the symmetric function that we're looking at to begin with, where we got these a's from. So it turns out that this element G is the element such that yq of G equals the symmetric function we had in mind. So for any symmetric function, we can find a group algebra, find a Hecke algebra element G such that yq of G is our symmetric function. So as a corollary, we plug in q equals 1. Each symmetric function, which is homogeneous to degree n, equals y of G for some G in the symmetric group algebra. Actually, we have to let the coefficients be rational. And one choice of such an element is G equal to, I guess we have to write the symmetric function in terms of the elementary basis first. So one choice of such an element is obtained by writing our symmetric function as the sum of a lambda e lambda, and defining G G basically like this. We're going to take the coefficients and put them in the numerator. And then in the denominator, we're going to take all the parts of mu factorial, but with no q's, and multiply each one by the Krajnow-Lustig basis element evaluated at 1. So that means that pretty much every symmetric function we might look at has coefficients, whether you expand it in elementary basis or the monomial basis or the Schur basis. It's got coefficients that are induced sign characters of something, or monomial traces of something, or irreducible characters of something. So every symmetric function is basically a generating function for character evaluations of something in the symmetric group algebra if the coefficients are all integers, or in the Hecke algebra if the coefficients are polynomials in Q. The end.